this is AP Precalculus, notes for topic 2.1, change in arithmetic and geometric sequences. Let's dive in. All right, so when we're talking about these arithmetic and geometric sequences, we want to first talk about a sequence. So what is a sequence? A sequence is a function where you plug in whole numbers, so from the whole numbers, and it outputs some sort of real number. So that means that you can plug in whole numbers into a sequence. For example, if I have a sequence of, 3, 4, 5, I can say the first number is 3, the second number is 4, the third number is 5, but I can't say the first and a half number because there is no first and a half number. All right. As a result, when we graph a sequence, we will have points, but we cannot connect them together. So before we had something that was called continuous, where we could maybe make a line. So we'd have something that looks like this, a line, but now we're going to have a bunch of points because they're going to be discontinuous, or it is sometimes called discrete. So in example 1, we're going to consider the sequence that's defined by, and this is how we read this function. We say that this is a sub n, so each term, each nth term is just 4n minus 3. So to find the first term, we're going to do 4 times, I guess I should write this out further. I can say to find the first term, a sub 1 is the first term. You take that 4n minus 3 and switch out the n for 1. This is 4 times 1 minus 3. And that means a sub 1 is going to be 4 times 1, which is 4. And then a sub 1, therefore, is 1. The first term is 1. They happen to be the same number as the term number. That's okay. And find a sub 7. So a sub 7 is the 7th number in the sequence. The 7th number, again, I just plug in 7 for n. I get 4 times 7 minus 3. And that means the 7th term is 28 minus 3. And that means the 7th term is 25. All right. So we're going to be studying arithmetic and geometric sequences. The first 2-ish pages are about arithmetic sequences. The next 2 pages will be about geometric sequences. So in every single sequence, we always talk about the property of successive terms. So arithmetic sequences have a common difference. Usually if I have a bunch of values, maybe I'll say, I'll have a bunch of values here with a bunch of commas. In order to find the common difference, it's this number that we're jumping by. The way that we can find that is you can technically do the right number minus the left number. Or you can say, you can ask a question another way, how much do I have to add to this number to get to that number? Okay, this jump is that common difference. And the key part here is it's a difference, therefore there's a subtraction sign. That will change when we get to a geometric sequence. So there's 2 formulas. This one is used less common. This is kind of the king or queen, depending on your gender, of the formulas. It's the one that you're going to be using all the time. And notice that you can actually get this original formula if you plug in 0 for k. So if k is 0, this is a sub 0, a sub 0. And if k is 0, then this k is 0, which means it's just d times n, which is that d times n. This formula is better. This one is faster if you know the initial value. So what is a sub 0? It is the initial value. D, we already know, is the common difference. And a sub k is the kth term in the sequence. So I'll just say kth term. So interesting notes. Arithmetic sequences behave like linear functions. They behave like lines. Increasing arithmetic sequences increase equally with each step. So it's like the slope that always stays the same. So I kind of think of the common difference as the word slope here. It's not really the slope, but it's the way that I understand slope. Same thing for lines. So here's an example. I want to be able to graph this sequence. A sub n is equal to 3n plus 1. The first thing I'm going to do is I'm going to make a table. So this is the nth term, and then this is the actual nth. So I guess this is the term number, and then this is the actual term itself. So I want term number 0, term number 1, term number 2, term number 3, etc., etc. So when I plug in 0 into n over here, that means a sub 0, right? 3 times 0 is 0. And then 0 plus 1 is 1. I can say the 0th value is 1. That means if I go to the n coordinate, or the old-fashioned x coordinate, right, I don't go any to the right. I'm just at 0. I go up to the height of 1, and I can graph that on my graph. Again, we are not going to connect these points. This is a discrete function. It's a sequence. All right, so what happens when I plug in 1? So when I plug in 1 over here, it's going to be 3 times 1, which is 3, plus 1 is 4. When we plug in 2 for n, it's going to be 3 times 2, which is 6. 6 plus 1, 7. And by now you can kind of see the pattern that's happening over here. To get from 1 to 4, I'm adding 3. To get from 4 to 7, I'm adding 3. This pattern holds, and you keep adding 3 over and over, and this is going to be 10 over here. If you don't believe me, you can plug in 3 for yourself. Let's go ahead and graph all of these. So I have 0, 1, I've already graphed. 1, 4 lives right here. 2, 7 lives right here, and then we're off the graph. Notice that I'm not going to connect these with a straight line because it's not continuous. It's just a bunch of points, and there is no, what is the 1/2 value, right? All right, so example 2. For each of the following, determine if the sequence could be arithmetic. And if it is, then identify the common difference. So it's kind of a giveaway. Like, I told you that arithmetic means that it has to be linear. Is that a linear function? No, silly. That's a quadratic. It's a power of 2. So just by knowing the type of function, I can say no. But what if I didn't know that? What if I'm like, I'm not sure? Go ahead and make a table using the nth, like the term number, and then the actual term itself. They're using s this case instead of a, which is weird, but we'll go with them. Okay, s sub n. So let's plug in like 0, 1, 2, 3 values is probably enough to see if it's arithmetic or not. So when I plug in 0, I'm going to get 0 squared minus 3, which is -3. When I plug in 1, 1 squared is 1, 1 minus 3 is -2. And when I plug in 2, 2 squared is 4, 4 minus 3 is 1. And then we'll look at these successive first differences. So to get from -3 to -2, I add 1. To get from -2 to 1, I add 3. And notice that these values are not the same. Therefore, it is not arithmetic. So in part B, we were just analyzing this function. That looks like a line function. It's a linear function. A linear function is arithmetic. So I can automatically say yes and just cheat by knowing the types of function. But again, how would I do this if I didn't know how to analyze a function? I would plug it into the table. So the table, again, nth term, and then the actual term number and the term itself. So term number 0, term number 1, term number 2, that should be plenty. So what happens when I plug in 0? It's going to be 6 minus 2 times 0, which is just 6. 6 minus 2 times 1 is 4. 6 minus 2 times 3 is 2. Sorry, 2 times 2 is 2. There it is. And then what are the differences? To get from 6 to 4, I subtract 2. To get from 4 to 2, I subtract 2. And you can see, oh yes, look, these common differences are all the same. If they're all the same, then it is an arithmetic sequence. All right, what about part C? Again, it basically did the table for us, so let's go ahead and analyze these jumps. To get from -7 to -2, I add 5. To get from -2 to 3, I add 5. To get from 3 to 8, I add 5. And to get from 8 to 13, I add 5. So this one is also a yes. This one is arithmetic. I'm realizing that we didn't answer the second part, which is if it is yes, which this one was, then we need to identify the common difference, aka the variable d, right? We've been using d for common difference. The common difference is this number that we've identified over here, this -2. All right, and then over here, I can say that the common difference, we have analyzed it over here. It is +5, so I can say it's just a +5. And then what about over here in part D? In part D, take from 1 to -2, I go down 3. To get from -2 to 3, I go up 5. And immediately I can say no. These all have to be the same number. Otherwise, it's not arithmetic. So the answer here is it's not arithmetic. All right, moving on to example 3. We're saying a sub m is an arithmetic sequence, and we know that this is how I'm going to read this. The third term is 8. So here, let me draw a picture to make sure you understand what's going on. What we have is we have the first term here. So we'll say a sub 1 goes there. We have the second term there, a sub 2, and we have the third term here. We don't know the first term. We don't know the second term. Hey, but we know the third term is 8. We'll put question marks for it here. So the sequence is blank, blank, 8. And we happen to know to move to each next spot, the common difference, D here, is we go down 3. So that's all we have so far. And we need to find an expression for a sub n. And once we have that, use it to find a sub 12, the 12th term. So first we're making a formula. And this is where we're going to refer back to our notes where we use this king/queen of formulas. This is the exact formula that I'm going to be using. So I have that memorized, and you need to memorize it as well. The general idea here for the formula is you say a sub n is equal to, you choose a term, any term. We only have one term, so I'm going to write that term down. And then we add the common difference. So I'm going to plus the common difference. The common difference is -3. We'll fix the plus minus in a sec. And then you're going to multiply by n minus whatever that term number was. This is the eighth, or this is not the eighth term. This term is 8 and is the third term. So this 3 is going to go in here for n. And there's our formula. I mean, I can simplify it a little bit and I can say, okay, really it's a sub n is equal to 8 minus 3 times n minus 3. All right, and now we're going to use that to find the 12th term. So I'm going to say, okay, a sub 12 is going to be equal to, I'm going to rewrite that formula, 8 minus 3 times, not n anymore, but 12 minus 3. All right, what's that going to be? It's going to be 8 minus 3 times 9, which is going to be 8 minus 27, which is going to be negative 19. So I can say that a sub 12, or the 12th term here, is 19. Ooh. All right, example 4, a little bit harder. And why is it harder? Let me draw a picture of what's happening. There's an arithmetic sequence. I have the first term, second term, third term, fourth, fifth, sixth, etc., right? So I'll say that this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and a sub 6. We happen to know that the second term is 7. And we happen to know that the sixth term is 9. The question is, what's the formula? What's the expression to get a sub n? And use that formula to find the 24th term. I mean, you can probably just use guess and check now that I've drawn a picture, but what if it's a really disgusting number? Like, you're supposed to add 5/7 each time. How would you know how to do that? And there is a way to do that, and the answer is slope. Slope always works for arithmetic sequences because it's essentially a line. So I'm going to invoke that definition of slope, and I'm going to put slope in air quotes because, or I guess real quotes, because it's not really slope. Slope is for a linear function. This is technically an arithmetic sequence, which is similar but not necessarily the same. Our old definition of slope was the change in y over the change in x. So our new definition here, I'm going to call this the common difference, d, is going to be the change in the actual term number, so of the a values, divided by the change of the actual term numbers. So in this case, how much do my change in numbers, whoa, I didn't mean to double tap with my palm there. The change in number, oh my goodness, my change in numbers, is double tap is set to erase. I need to turn that off. The change in numbers, I went from 7 to 9. So I'll try to color code this. This is going to be in blue. To get from 7 to 9, I went up 2. So this one is going to be plus 2. And then to get from the second term to the sixth term, I went up 4. So this is going to be plus 4 for the term numbers. And then this fraction here is going to be a positive 1/2. And that is the common difference. And again, we're going to use that king/queen of formulas. And we're going to say, okay, to get any a sub n, we take any term. I could choose the 9th term. I could choose the 7th term, or that's not the 7th term. I could choose the term of 7, choose the term of 9. I could choose the 6th term or the 2nd term. It doesn't matter. I'm just going to arbitrarily say, I'm going to choose this number 7. Okay, 7, the 2nd term. And then I add the common difference, which we just found. So I'm going to go ahead and say this common difference is coming down right over here. The common difference is 1/2. And then I'm going to multiply it by n minus, what was the term number? This is the second term, that is 7. The second term is 7, meaning 2 goes in over here. So we have 2. So we have our formula now. From here, we're going to use our formula to find the 24th term. So how do we do that? We say a sub 24, the 24th term is, we just rewrite all this, 7 plus 1/2 times, and then instead of n, it's going to be 24 minus 2. Simplifying, this is going to be plus 1/2 of 22. There's a 7 out there. There's the 24th term right there. Oop, that's not 24th term. There's the 24th term. Half of 22 is 11. And 7 plus 11 is 18, which means the 24th term is 18. Excellent. All right, moving on to example 5. We have a graph up here. Several terms of an arithmetic sequence a sub n are shown above. Find an expression and use the expression to find the 17th term. So it's the same thing, but the information is in a graph this time. All right, so again, we're using that king/queen of formulas. And we're going to say a sub n is equal to, okay, I choose any term that I want. This is the 0th term, and the value is 8. The value is 6, the value is 4, the value is 2, the value is 0. Any of those work. And to prove it to you, I'm going to randomly choose that one. Okay, so I'm going to circle that so I can remember. That's the value that I'm choosing. So the actual term number is 4. And then I have to add the common difference. So notice that I'm going down to right 1. You're kind of making those step ladder type rungs. So I'm going down to right 1, which means I'm going down to right 1. I guess I can just say it's a slope of -2. Here, let me rewrite that and say it's a slope of -2, and I do n minus the term number. So this is the term 4, and it is the second term. So this is n minus 2. And there's a formula. There's a bunch of formulas I could have chosen. That didn't have to be the only one. And I'm going to use this now to find the 17th term. I'm going to say a sub 17 is equal to, and this is going to be 4 plus, I guess not really plus, is it? It's subtract 2 times and then 17 minus 2. Okay, this is going to be 2 times 15. And this is going to be 4 minus 30, which is going to be negative 26. So the 17th term here is 26, negative 26. Excellent. All right, moving on to geometric sequences for the next 2 pages. So again, now we have a common ratio. So essentially what's happening here, let me make sure that my notes over here were accurate. Over here, we were adding each time, plus, 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 or I guess subtract, subtract, subtract. We're adding a negative, right? Now, in this case, when I have a bunch of numbers in my sequence, to get from one term to the next term, I'm going to figure out what I'm multiplying by. Multiply by 2, or something like that, right? In order to figure out what that common ratio is, it is the ratio of the right number divided by the left number. That will always give us the common ratio, which we are calling R, so I can fill that in right now. This is the common ratio. Again, this is the, I'm going to just say king of formulas, because you can always rederive this initial formula up here. This is another formula that you have to have memorized, and g sub 0 is the initial term still, and g sub k is the kth term in the sequence. All right, so interestingly, this is an exponential function. Exponential functions that are still not continuous. Again, we are in the discrete land, just a bunch of points, no lines. And increasing geometric sequences increase by a large amount at every single step, or decrease by a large amount each step, depending on the type of ratio that we have. But this is interesting. This is the fact that will probably help us solve some future problems. The percent increase will always be the same. You're always increasing by a factor of 50%, increasing by a factor of 50%. That means anytime you have a constant percent increase, you're really talking about a geometric sequence. All right, so I have this geometric sequence right here. Notice that it looks very similar to this form. Again, just pointing out some differences between the geometric formula and the arithmetic formula. Before, we had a plus sign in between the term out here and then this stuff over here. Now it's a multiplication because we're multiplying each time. Another thing to point out is this is now up into the power instead of being multiplied. It used to be down here and being multiplied. Now it's up here in the power. All right, so this is indeed a geometric sequence, which is kind of like an exponential function. I'm going to make a table to make this easier to see. So this is the nth term, and then this is the actual term number, which we're going to say g of n. So let's plug in 0, 1, 2, 3, 4, etc. When I plug in 0, notice what's going to happen. This n is going to be 0 because n is 0, right? So if this is 0, anything to the power of 0 is 1, and 8 times 1 is that 8. All right, moving forward, what happens when I plug in 1 to n? Now it's a half to the power of 1, which is just a half. A half of 8 is 4. Last one with plugging in until we just make sure we have the pattern down. If I were to plug in a 2 into n, then it would be a half to the power of 2. Just as a reminder, if I have a half to the power of 2, that's the same thing as saying 1 to the power of 2 over 2 to the power of 2, which is 1 over 4. If I have 8 times a fourth, that's the same thing as saying 8 over 1 times 1 over 4, and I multiply straight through. 8 times 1 is 8, 1 times 4 is 4, and this is really the question, what is 8 divided by 4? Which is 2. So it goes to 2, and you can now see, oh, to get from each step to the next, you are, and I'm going to purposely make a mistake that most students see, oh, you're dividing by 2. You're right, it is divided by 2. But because we defined a common ratio as what are we multiplying by, you have to say multiply by. I'm forced to say multiply by something, we're multiplying by a half. Multiplying by a half. And this pattern continues on and on. So multiplying by a half, multiplying by a half. So 2 times a half, or a half of 2 is 1, half of 1 is a half. Let's go ahead and graph these and see what shape we get. I'm going to plot 0, 8, plot 1, 4, plotting 2, 2, plotting 3, 1, and attempting to plot 4, a half. And again, I'm not going to connect these with a line. This is discrete. This is just a series of points. That's all I can do. All right. Example 6. For each of the following, determine if the sequence could be geometric. And if it is, identify the common ratio. I'm guessing it's saying common ratio. Yes. So again, I know what an exponential function is. An exponential function has the variable in the exponent, therefore the name exponential function, right? In this first function, it might look like an exponential, but really it's a power of 2. If I switch the 2 and the n, then it would be exponential. The power has to have a variable. This is technically a quadratic, not an exponential. Therefore, I know just by analyzing the function, the answer here is no, it's not going to be geometric. And to prove that to you, I'm going to make a table. So let's make a table of the nth term and the actual term itself. So let's check the 0th term, the first term, the second term, etc. Right? You really only need to check 3, and then you should be good. So if I plug in 0, it's going to be, what do we have here? 0 squared, which is 0, and 0 times 3 is 0. Okay, that makes it difficult to multiply anything by, but here we go. If I plug in 1, 1 squared is 1, times 3 is 1. When we plug in 2, 2 squared is 4, 4 times 3 is 12. All right, so the question is, what are we multiplying by? Because this is all geometric, right? Well, to get from 3 to 12, that's clearly multiplying by 4. But how do I get from 0 to 3? 0 times anything is going to be 0, so you can't multiply by anything. So because you can't get from 0 to 3 with multiplication, the answer is no, you can't be a geometric sequence. All right, what about B? Notice that it has a variable in the exponent, therefore this is an exponential function, and therefore we can say right now, yes, this is a geometric formula, therefore I am going to find some common ratio. Let's pretend that you didn't know how to do that analysis and you just made a table. So n and s of n. What happens if I plug in 0? Ooh, I don't want to plug in 0, because if I plug in 0, I can already see what's going to happen. I'm going to get a negative. I don't want to deal with negative. I know how to do it, but I'm trying to be going as fast as possible. So I'm going to go here and say that this is going to be, let's plug in 1. Yeah, 1, 2, and then 3. So when I plug in 1, I purposely chose it because it's a nice number now. 1 minus 1 is 0. Anything to the power of 0 is 1. So that's all 1. And the answer here is just 4. All right, now what happens if I plug in 2? Plugging in 2 is going to make this 2 minus 1, which is the power of 1. 2 to the power of 1 is 2, and 2 times 4 is 8. So this is going to be 8 down here. And then when I plug in 3, 3 up here is going to be 3 minus 1, which is 2. 2 to the power of 2 is 4. 4 times 4 is 16. And we have our table done. Notice to get from 4 to 8, I have to multiply by, wait, did I did this right, yeah. So multiply by 2. And to get from 8 to 16, multiply by 2, which actually makes a lot of sense because the base of our exponential function is 2. Whatever that base is should be the common ratio according to our formula up here. This base right here is the common ratio, r. All right, so yes, it is a geometric sequence and that common ratio is 2. What about the next one? The table's already kind of laid out for us. I can say if you get from 1 to 3, I multiply by 3. To get from 3 to 2, you don't multiply by 3, technically multiply by 2/3. These two numbers are not the same. Therefore, the answer here is no, it's not geometric. What about D? I doubt it, but let's take a peek. To get from 16 to 8, I take half. So I say half of it, but it switched between negative and positive, so negative half. To get from 8 to 4, oh, I also take a half, and it's switched back from negative to positive, so it's technically multiplying by negative a half, multiplied by negative a half. Again, multiply by negative a half, and again, multiply by negative a half. Okay, so it was geometric, so I'll say yes. And the common ratio here is negative a half. Nice. All right, number 7. We have a geometric sequence where the first value is 12 and the common ratio is 2. All right, so I don't even need to draw a picture. I can clearly see what's going on here. We're just making a formula, and then we're going to use that formula to find the fourth value. So the formula generally looks like this. G sub n is equal to the term. So it's saying that the first term is 12. The 12 is the term. I'm going to put that over here and say 12. Okay. I'm not going to add this time. I'm going to multiply. Everything in geometric sequences are constantly multiplying. Everything with arithmetic, the old ones were constantly adding or subtracting, I suppose. Adding a negative, I'm going to say. So it's always adding, right? So we multiply by the common ratio. The common ratio in this case is 2. It tells us that right here. And then this is going to be to the raised to the power to the n minus whatever our term number was. This is the first term, so it's going to be n minus 1. Formula's done. We're going to use the formula now to find g of 4. So to find g of 4, I'm going to take 12 times 2 to the power of 4 minus 1. This is going to be equal to 12 times 2 to the power of 3, which is going to be 12 times 8, which is going to be 96. So the fourth term here is 96. All right, what about in example 8? We have a a graph up here, and we need to find an expression and use it to find the 10th term. Interesting. Okay, so what do we notice is going on in this table? It's clearly geometric because having that shape where it's going down like an exponential function. How do I get from a height of 8 to a height of 4? What am I multiplying by? So I'm already seeing to get from here to here, I'm multiplying by a half. So that means that my common ratio here is a half. Okay, I can choose any term that I want. I can choose the 0th term, the first term, the second term, the third term. I kind of like choosing the 0th term because I'll have a 0, and zeros are probably going to be really nice. So I'm going to choose u. I'm going to circle u. Okay, so to find our formula, g sub n, I'm going to take our term, which is 8, and I'm going to multiply by the common ratio, which we actually know it's not r, it's a half, and that's going to be raised to the power of n minus the term number. We said that the term number is 0, not 1, not 2, but 0, therefore n minus 0, which I could have just said n. Okay, now I'm going to use that to find the 10th term. So g sub 10 is going to be 8 times a half, and that's going to be raised to the power of 10. All right, so what do we have here? This is going to be 8 times 1 to the power of 10 over 2 to the power of 10, which is going to be 8 times 1 over 2 to the power of 10. That's technically over 1. So this is going to be multiplying straight through as 8 on the top and 2 to the power of 10 on the bottom. Ooh, I can use a properties of exponents. Check this out. Okay, 8 is the same thing as 2 to the power of 3, and 2 to the power of 10 stayed behind. When you have the same base, you're doing this power struggle, right? Which of these powers is the most positive? Which one is the biggest, right? Well, the bottom is biggest, therefore the answer is going to be in the bottom. 2 is going to be in the bottom. Nothing's left over in the top, so I'm just going to leave a 1. And then I subtract the powers. Division means subtract the powers. 10 minus 3 is 7, so it's 1 over 2 to the power of 7. That's the answer. I mean, I could simplify it a little bit more. 2 to the power of 7, what is that? It's going to be 1, 2, 3, 4, 5, 6, 7. That's 4, 8, 4, 8, 8 and 8 is 64, 64 and 64. So those two are 64, and then I have to do that 2 and that 64, 128. So it's technically 1 over 128, but I like 1 over 2 to the power of 7 because it showed off the fact that I was using powers of 2 and being clever. All right. We have the part 2 of the notes, which is a much needed addition, an extension of our existing problems, which is obviously a little bit more difficult. The first one is actually easier than all the other problems. We have a geometric sequence, and we only need to find an equation. You don't even need to find any value. So the equation, again, for g sub n, you take any term that we're given. Our term is -3 in this case. We multiply by the common ratio, which it tells us is 10. Raise it to the power of n minus whatever the term number is. In the case, it's 3. And we're done with example 1. Look how easy that was. All right. In example 2, it's a little bit more tricky. We say that the second term is 24 and r is equal to the 1/2. This is what we were kind of doing in the previous page. We could say, okay, g sub n, what term are we given? 24. Multiplied by the common ratio, which is 1/2. And it's going to be to the power of n minus the term number, which in this case is 2. We have a formula and we need to use it to find the fifth value. So g sub 5 is going to be 24 times 1/2 to the power of 5 minus 2. So it's going to be 24 times 1/2 to the power of 3, which is going to be 24 times 1/8. I skipped a step there, but I think everyone can see 1 to the power of 3 is 1, and 2 to the power of 3 is 8. And then this is the same thing as 24 over 1. That's going to be 24 over 8, and 24 over 8 is just 3. So you can say, there's our final answer. It's a little bit convoluted there, but we're good in the end. Okay, this next part is really, really tricky. So I'm going to temporarily ignore this because those words are a little bit confusing to me. I mean, they're great steps, but I want to show you a picture to help you create an equation. It's like, yeah, just make an equation. It's hard though. Draw a picture. That's what helps me. So here's my picture. I have 6 values. 1, 2, 3, 4, 5, 6 values. This is going to be g sub 1, g sub 2, g sub 3, g sub 4, g sub 5, and g sub 6. We happen to know that g sub 3 is -2. We happen to know that g sub 6 is 128. That's all the information we're given. We need to somehow find a common ratio from this. And you could probably guess and check it, but I promise you it gets really, really hard. Like in example 4, I mean, I could still kind of probably guess that one if I'm really good at guessing, but they get really hard. There needs to be some sort of systematic way of doing it. So the cool thing about geometric sequences is they're constantly multiplying by the same number with every single one of these jumps. This is multiplying by r, multiplying by r, multiplying by r. So here's how you make an equation. I'm telling a story in words, and then I'll make it into an equation. I started with -2. I multiply by r 3 times, and then once I was done with that giant multiplication problem, I got 128. Here's how you do that. You say, I started with -2. I repeatedly multiplied by r 3 times. There's actually a shortcut for repeated multiplication. It's called an exponent. Whenever I do a power, this is really r to the power of 3. So this is going to be r to the power of 3. And I got from that 128. Now I've set up an equation, which is what part 1 was asking us to do up here. And now we're going to do step 2, which is to solve for r. To solve for r, I'm going to get rid of this -2 on both sides. I'm going to say divide by -2. I don't need to write that. You know that I'm dividing by -2. So I'm now going to get r to the power of 3 is equal to -64. From there, I need to undo the power of 3. Well, yes, you would be correct if you said, well, you just cube root both sides. You are 100% correct. That undoes the power of 3. But because eventually these numbers are going to be like power of 17, technically it is the 17th root, but those 17th roots are kind of hard to find on the calculators that we're using. I'm going to show you a little bit of a faster way. The way that I prefer to do this is to the power of 1/3. Because check it out. If I have a power to a power, I multiply the powers. 3 times 1/3 is 1, and it's just gone. So if I take the left side to the power of 1/3, the right side is also taken to the power of 1/3. And therefore, I can come down here and say r is equal to the cube root of 64. This is saying the same thing as the cube root of 64. I happen to know that that's 4 off the top of my head, but if you didn't know that, you could always use a calculator. I hope. I don't know which are calculator questions and which are not. I'm still new to this AP Precalculus thing. R is equal to -4, which is crazy. That was the hardest part of this problem. Now that we know that the common ratio is -4, then we go ahead and use that to write a general form, which is what it's telling us to do right now. We're going to write the general form of the equation. We're going to say g sub n is now equal to any term I want. I'm just going to randomly choose -2. And then I'm going to multiply that by r, which we had a fight to find. That was -4. And that's going to be to the power of, and I had to put parentheses because there is a negative. Always be careful of negatives. They have to have parentheses. Otherwise, your order of operations might get messed up. This is to the power of n minus whatever term number. This is the third term, so I'm going to say n minus 3. We now have our general formula, and we can use it to find this 11th term. I can say g of 11, now we're ready to find you. It's -2 times -4 to the power of 11 minus 3. Oh, I can see this being really big. I don't know if I can do this without a calculator. This is going to be -2 times -4 to the power of 8. I don't know what -4 to the power of 8 is. It's a really big number, but I'm just going to be lazy and be like, yep, there it is. It's a problem for another day. I assume this is a calculator problem. I'm just going to cheat here. I'm not going to cheat. I'm going to use a calculator. I'm on, there we go. So my calculator, I'm going to say is -4 to the power of 8. Well, the negative doesn't matter because it's a power of an even. So I'm just going to say 4 to the power of 8. So 4 to the power of 8 is going to be, oh my goodness. It's going to be -2 times 65,536. And if I multiply that by 2 because I'm feeling lazy, it's going to be negative 131,072, which is 131,072, which is my final answer after using the calculator and showing you how to use tools appropriately, right? That's a better way of saying that. I have a feeling that I'm going to use a calculator on this one. I'm just going to leave it up. Example 4, the last problem of our notes. Here we go. We have a geometric sequence, and that stuff is happening. So again, it really helps us to draw a picture. So we have 1, 2, 3, 4, 5, 6, 7 things happening. Here's g of 1, g of 2, g of 3, g of 4, g of 5, g of 6, g of 7. I would try to stress that you should be able to start doing these without using a picture. In fact, I will come back to the picture to verify my work. Let's see what happens without that picture. I have it ready to be set up. I know that I'm going to start with 48. I know I'm going to be multiplying by r some number of times. And I know that's going to be, so there's some number that's going to go up there, right? And that's going to be equal to 1.5. That's the general setup of my equations. I just don't know how many jumps did I take to get from 48 to 1.5. Well, I had to jump from 2 to 7. Look back here. To get from 3 to 6, I jumped 3 times. It's really just 6 minus 3. You just subtract them, right? So 7 minus 2 is 5, and this is going to be 5 jumps. Let's check the picture and make sure that that makes sense. So over here, the second term was 48. Whoa, accidentally double tapped the pencil, I guess. 48. And the seventh term was 1.5. So I jumped 1, 2, 3, 4, 5 times, so that makes sense. It is a power of 5. Now that this is all set up, I'm going to solve. So I'm going to divide both sides by 48. And I told you we're going to use a calculator. I have no idea how well, I do have an idea of how you do this without a calculator. It's not fun though. All right, so from here, divide by 48, and r to the power of 5 is equal to 1.5 divided by 48. It's a problem for the calculator. We're just going to leave it like that for now. And then we're going to get rid of 5 by taking both sides to the power of a fifth. Both sides to the power of a fifth. Therefore, this is why we have a calculator. R is equal to, let's plug this in parentheses, 1.5, that's a 2. 1.5 divided by 48. All of that to the power of, and I'll say to the power of, and then in parentheses again, 1 divided by 5. Boink. 0.5. 0.5. Which again is the same thing as writing in half. You can choose whichever one you want. You want a decimal, you want a fraction, whatever floats your boat or sinks us up, right? Okay, we have the common ratio. It's now time to use that in the general expression. Calculator, I think we might have needed you. Oh yeah, we might have, okay, I messed up there. We're trying to find g sub n first, and then we're gonna find the 11th value. I can choose any term that I want. I typically like the one that's over on the left more, but that's up to you guys. So I'm gonna say 48, and then I'm gonna multiply by the common ratio, which we found is a half. I prefer fractions. And this is going to be to the power of n minus whichever term we use. This is the second term, so I'm going to write a 2 over here. And I have my formula. Now we're going to plug this in. I'm going to say, okay, g of 11. The 11th term here is 48 times this 1/2 to the power of 11 minus 2. And this is going to be equal to 48 times a half to the power of 9. I think I can do this without a calculator. This is doable, right? How would I solve this? This is going to be equal to 48 over 1 times 1 over 2 to the power of 9. And I know just off the top of my head that this is a good fact to remember, that 2 to the power of 10 is equal to a megabyte, 1024. And if I divide that by 2, I get 2 to the power of 9, which is equal to 512. So that means that the bottom is 512. And I really just have the fraction 48 over 512, which I need to reduce. I go slow, guys. I'm sorry. I divide by 2. I get 24. And I get 256. I can divide by 2 again. Okay, divide by 2. I get 12 over 100 and what is that? 28? 128, I think. And I can divide by 2 again. Divide by 2, and I get 6 over 64. I think I can go one more. Divide by 2 again. I get 3 over 32. I hope that's okay. Back me up, calculator. I don't trust my math skills. There's too much math there at the end. All right. What is 48 divided by 2 to the power of 9? What is 3 divided by 32? Are they the same thing? Let's go! I got it right. They're the same decimal. All right. Told you I didn't need a calculator. I just used it to check my work, which is what you're supposed to use a calculator for, right? That concludes our notes for AP Precalculus topic 2.1 for geometric and arithmetic sequences. Thanks for watching.